Hi, our group project that we're gonna be presenting today is about a deep learning network and the training and implementation of it to recognize written digits in MNIST and produce out a 28 by 28 pixel image as a result. Our team members consist of Pamphlit Paripan Pishavut, Niman Tangsit Seriwong, and Tanison Salim. I'll be going over the libraries used and the functions that are used to set up the neural network. So first, we have random, which is used to shuffle the training data, and then we use NumPy for creating weight matrices and bias vectors. Then we use PyTorch and Transform to download MNIST data and then convert it into tensors. Then we have Matplot, which is for plotting data and images for the last part of the result. And then we have PyTorch utility, which is used to reduce the MNIST dataset for faster training of our model. Our first function is the initiate function, which is used to set up the structure of the neural network. The sizes is a list that represents the number of neurons in each layer, and then we find the length to find the amount of layers. Then we create self-bias, which is used to create a bias vector for every layer, and we start from 1 because our input layer doesn't have biases. Only the hidden layer and the output layer has biases. Then we use self-weight to create a weight matrix between each layer. All of this is used to set up the parameters for the neural network. Our next function is the forward pass, which is used to take an input vector from MNIST and then computes the network's output, which is how the neural network thinks. So first, A is the activation vector, and then it goes through a linear transformation which pairs the weight matrices and the bias vectors to create a weighted sum of C. The sum C is then put into the sigmoid function, which squeezes each value between 0 and 1. And this value then becomes a new activation, which is then looped through one layer into the next. The final output for this is a 10 by 1 vector, which each entry represents how strongly the network thinks. The input is a particular digit. Our next function is the SGD, or the stochastic gradient descent, which is the main training loop for our neural network. So first we have training data, which is the list of training samples. Then we have epoch, which is how many times to train the entire dataset. The batch size is the number of samples. ETA is the learning rate. And then the test data, which is the optional test to measure the accuracy of each epoch. So first we check if the test data exists. If it exists, then nTest gets the number of test samples and then store the total number of training samples in n. Then we have the epoch loop, which repeats the training process. We use random shuffle, which is used to shuffle the training samples to prevent the network from learning patterns from ordering. And this is better for the SGD performance. Then we have mini batches, which breaks the training data into mini batches, which makes the gradient easier because it's not using the whole dataset, but it's using small random samples. This loop produces a list of smaller batches. Then inside we have a loop over mini batches, which is for mini batch in mini batches. It goes through every mini batch and then updates the mini batch with compute gradients and then updates the weights and biases using the learning rate. This is the actual learning step of the neural network. the last part is the evaluation, which if there is test data, then it will print out self-evaluate, which is the predictions of how many were correct, and it prints out for you to see for tracking. And if there were no test data, then it will print out complete.
My name is Nimman Tangsisewong, and I'll be presenting these two functions, update mini batch and the backprop. So, update mini batch collects the gradients from every training example inside the mini batch. It starts by creating zero matrices, which is the empty array, basically, shaped like the network's weights and biases. For each input in the batch, it calls backprop function to compute how the cost changes with respect to every weight and bias. These gradients are added together. After the batch is processed, the function updates the weights and biases by subtracting the learning rate times the average gradient. This step moves the networks in the direction that reduces the cost, allowing it to learn and improve its predictions. Next step, the backprop function. It computes the gradients of the cost function with respect to each weight and bias in the network. And this is the cost function. It can be expressed in many forms, but in this project, I choose this form because it's the easiest. So, first, it performs a forward pass through all layers, computing the weighted inputs, which is this equation: z equals weights multiply a plus bias, and activations, which is a equals sigmoid function. So the activations or the variable a is the output. We store these values for using the backward pass. At the output layer, the error is calculated as this equation. The delta or error equals to nebula c element y multiplies with sigmoid prime, where nebula c is a derivative of cost function with respect to activation output, and sigmoid prime is a derivative of sigmoid function to z. This equation comes from the chain rule of partial differentiation. Then, the gradients for the output layer are then nebula b equals to delta, like this equation, and nebula w equals to delta multiplies with activation, like this equation. The function then backpropagates this error through the hidden layers using this equation, which is delta from the previous one equals to the next one weights multiplies with the next one delta element wise multiplies with prime sigmoid function, which is, again, this delta is from the chain rule. Calculating delta nebula b equals delta and nebula w equals delta multiplied with the activation for each layer, the same way we did it. Finally, nebula b and nebula w store all these gradients, which are returned to the update mini batch function. In update mini batch, the weights and biases are updated according to this equation, which is new weight is equal to previous weight minus zeta, or learning rate multiplies with average nebula w. And we'll do the same thing with the bias, where m is mini batch size, of course, for these equations. This process implements stochastic gradient descent, iteratively adjusting the parameters to minimize the cost function and improve the network's predictions.
Evaluate function. It tells how many test images the neural network predict correctly. The process is first for every sample XY in the test data, it performs two actions. First, the prediction. It runs the input X through the network self X and finds the index of the highest output activation using NP argmax. This is the predict digit, and then true labels, which finds the index of the 1.0 in the one hot encode true label y using NP argmax y. This is the true digit. And then it compares these two indices, and finally it sums up the total number of correct matches across the entire dataset to return the final count of successful classification. Causative function. The law is to detect the error. This is the starting point for back propagation, calculating how far the network's final output is from the target. Process is it calculates the simple difference between the actual output of the network and the true label vector, which the equation is either equal to output activation minus the true label. This function assumes the network is using a quadratic cost function, which is mean square error, where this difference represents the derivative of the cost with respect to the output activation. The sigmoid function. The law is to activate function. It introduced the non-linearly required for the network to model complex real-world data. The process is it takes any input value Z, which is the weight sum of inputs plus bias, and squashes into an output S between 0 and 1, which the equation is S equal to 1 over 1 plus e power of negative c. Sigmoid derivative function. The law is the gradient component. It calculates the rate of change of the sigmoid function, which is essential for adjustment rate during training. The process is it computes the derivative using the sigmoid function simple property, the pipette data function. The law is the input format. It converts raw data into the structured format required by the neural network for training. Process first the image flattening. It takes a 28 times 28 image and flatten it into a long 784 per one column vector X. Second, one hot encoding. It takes the single integer label and converts it into a tens per one hot vector Y, placing a 1.0 at the index corresponding to the true digit. Finally, it returns a list of these processed XY paths.
Our objective for this project is to build a functional neural network and to understand the process of it. It is to create a learning experience that we can experiment with different parameters and understand the mathematical steps involved with the training. And this project is aimed at helping us to understand how a neural network works, and more specifically in deep learning